Hello and welcome to the AICE Chemistry Lecture Series. Today we're going to cover section 2 of chapter 9, which we are going to talk about the effects of concentration on the rate of a reaction. Now that we talked about what rate is in section 1 and how do we calculate it from graphical and lab data, let's talk about how this correlation between the concentration and the rate of a reaction comes about, and how we can use collision theory to explain it. So let's get started. There are two factors that affect rate of reaction. One of them is going to be concentration, the other one is going to be temperature, which we'll cover in section 3. So let's focus on how temperature affects the rate. There are essentially two factors that can affect the concentration of a solution. One of them is the volume of that solution, and we can change that volume by diluting the solution and adding some solvent. And the other one is the moles of the solution. So in both situations, whether we are changing the volume of a solution to change the concentration, or we're changing the number of moles, what we're doing is that we are creating crowding when we increase concentration. So let's say we have a reaction or a volume of solution of two solutions that are mixed that are like this. If we increase the number of moles of that solution, we will get an increase in concentration. And that will look like this. It will be more moles in the same volume. If we instead decrease the volume by maybe say evaporating the solution, we would also increase the proximity of the molecules in that solution. A decrease in the volume of a solution of the solvent or an increase in the number of moles is going to lead to an increase in concentration and therefore cause those molecules to be closer together with less space between them. So whenever we increase the concentration of solutions and then mix them together to create a chemical reaction, what we're doing is that we're crowding the molecules that have to react. We're crowding the reactant molecules versus a less concentrated solution like we see here on the right side. The higher concentration leads to an increase in the number of collisions and therefore an increase in the number of successful collisions, which overall is going to lead to an increase in the rate of the reaction. Essentially, because the reactant molecules are more crowded together, we are going to have them crash into each other more often. According to collision theory, some of those collisions will be ineffective, some of them will be effective or successful. The more collisions we have over time, the higher the number of successful collisions we're going to get. So here we can see that by showing these kind of like starbursts around the successful collisions, whereas in the dilute, we would only maybe get 2 successful collisions because the molecules are much more spread apart. With a higher concentration, we will get more collisions and therefore more successful ones, which we can see here by the fact that there are 5 starbursts for successful collisions instead of 2. So because the higher concentration leads to a higher number of collisions, it also leads to a higher number of successful collisions, which have the right orientation and the right energy to create a reaction. The more collisions we get per second in a reaction vessel, the higher the rate of the reaction will be. The more collisions are successful, the higher the reaction rate or the faster the reaction happens. So this is why a higher concentration has a direct effect on the rate. The reason why higher concentration leads to a higher rate of reaction is because it creates crowding in the molecules and therefore a higher number of collisions and by default a higher number of successful collisions with the right orientation and the right energy. Now, with solutions, with aqueous solutions, concentration is really the only thing we can talk about. But when we come to gaseous solutions, we can talk about both concentration or pressure. Remember, we visited this concept many times throughout these 9 chapters. Pressure for gases is like concentration. For gases, concentration, and really for anything, gases or solutions, concentration is affected by volume and number of moles. So if we decrease the volume, we increase the concentration. If we increase the number of moles of the compound, we increase the concentration. Well, both of those have the same effect on pressure for gases. If we decrease the volume of a gas, the molecules are going to be closer together. And we can see that right here with this piston. The decrease in the volume, which would increase concentration, also decreases the space between particles of reactants, creating more collisions, causing an increase in the number of collisions and therefore an increase in the number of successful collisions. It also causes an increase in the collisions with the walls of the container. And that's because pressure will also go up. When we decrease the volume of a gas, we're not only increasing its concentration, we're increasing its pressure. So concentration and pressure for a gas, like we said many times, are going to be related to each other and have the same effects as each other. It's the same thing with increasing the number of moles. Increasing the number of moles has the same effect with molecules being closer together and therefore increasing the collision rate with the walls of the container, increasing the pressure. So increasing the number of moles not only increases concentration, it also increases pressure. So it's just to show you that pressure and concentration for a gas are going to be, basically have the same correlation with each other. As concentration increases, so does the pressure. That means that if you have a reaction with gases in it, pressure changes are going to have the same effect on rate as concentration changes because they're one and the same. Since both of these factors also increase the collisions between molecules, they're going to lead to higher rates of successful collisions and therefore a faster rate of reaction whenever we increase the pressure of a gas. So gas pressures and concentrations are one and the same and have the same effect on rate. When the concentration of a gas goes up, so does the pressure of that gas. And when the pressure or concentration of a gas goes up, the rate of the reaction also goes up. Because we already saw how how concentration and rate had a direct correlation with each other. Well, so does pressure if we're dealing with gases. All right. So this is just to show you that gases, when we mess with the pressure, it's going to mess with the rate of the reaction just like concentration would. And they're for the same basic reason. When we decrease the volume, the molecules are closer together, they crash into each other more often, and therefore the rate of the reaction goes up because we get more successful collisions. With number of moles, same thing. When the number of moles increase and the volume stays the same, the concentration goes up, also makes the pressure go up. And it crowds the molecules when we increase the number of molecules. The more molecules of a gas we have in the same volume, the more collisions we get, the more successful collisions we get, and therefore the higher the rate of the reaction. So that's it. This section is all about just explaining how collision theory can explain why as the concentration goes up, so does the rate, and for gases, how as the pressure goes up, so does the rate of the reaction. Obviously, this is concentration and pressure of the reactants, not of the products, because we are looking at a reaction as reactants creating products, not as an equilibrium reaction necessarily. So that's it. That is it for section 2. It's very short, sweet, and to the point. Just make sure that you can explain why as concentration or pressure of a gas goes up, rate goes up using the collision theory. That's it for today, and I'll see you in the next video.